All right, welcome to this explainer on the Kronecker delta. If you're studying engineering, physics, or applied math, you already know the struggle. As you transition into continuum mechanics and advanced vector calculus, writing out full matrices becomes incredibly tedious, right? Well, today we are going to fix that by mastering the ultimate index substitution tool.
Here's what we're looking at today. We'll start by defining the Kronecker delta, check out its identity actions on vectors and tensors, look at traces and dot products, cover some key identities and geometric meanings, and finally, wrap up with common mistakes.
All right, let's jump right in. Section 1. Defining the Kronecker delta, the identity operator in index notation. So, at its very core, the Kronecker delta is simply the identity operator, but written in index notation. You're probably already familiar with the second-order identity tensor. You know, big I, the 3x3 matrix with ones down the diagonal and zeros everywhere else. Well, in indicial notation, the components of this identity tensor are written as I sub ij, which is exactly equal to our star of the show, the Kronecker delta, or delta sub ij. Physically, it answers a remarkably simple binary question. Are these two indices equal? It gives you a 1 if yes and a 0 if no. Let's see how that binary question maps into the actual math. Mathematically, delta sub ij equals 1 when I equals j and 0 when I does not equal j. If you map this out into a component table across dimensions 1, 2, and 3, boom, you perfectly recreate that identity matrix. Looking at the numerical examples, notice that delta 1, 1 equals 1, but delta 1, 3 equals 0. Now this is absolutely crucial to remember. This symbol only checks index equality. It does not measure magnitude. It is literally just a matching game.
Moving right along to Section 2, Identity Actions on Vectors, introducing summation and the sifting property.
Okay, before we do the math, we absolutely have to define the Einstein summation convention. Basically, a repeated dummy index means we automatically sum over the spatial dimensions 1, 2, and 3. The rule is, when an index appears twice in a single term, like the j in delta sub ij times a sub j, you drop the summation symbol and just automatically add the terms together for j equals 1, 2, and 3. And this, my friends, leads us straight to the famous sifting property. Delta sub ij times a sub j simply equals a sub I.
Let's see this sifting property in action. In tensor notation, the identity matrix times vector A just equals vector A. In indicial notation, we write this as I sub ij times a sub j, which becomes delta sub ij times a sub j. Let's walk slowly through a numerical example with a vector whose components are 4, -2, and 7. Watch how the sifting property mathematically pulls out the matching component and just tosses the rest. If we set our free index, I, to 1, we get delta 1, 1, a1, plus delta 1, 2, a2, plus delta 1, 3, a3. Because only delta 1, 1 equals 1, the second and third terms just vanish. They become 0. That leaves us with 1 times 4, which is 4. Follow this exact same logic, and for I equals 2, the sifting property pulls out -2. For I equals 3, it pulls out 7. The Kronecker delta sifts right through the sum and perfectly reproduces the vector components.
Section 3, Identity Actions on Tensors, Left and Right Multiplication.
So, what about tensors? Well, in traditional tensor notation, if you left multiply or right multiply a tensor A by the identity tensor I, it simply returns A. Nothing changes. In indicial notation, left multiplication looks like delta sub ik times a sub kj, which just equals a sub ij. The dummy index k gets summed over, and the delta swaps out the k for an I. It's that simple. Let's prove it by finding the component for row 2, column 3 in our 3x3 matrix example. Set I to 2 and j to 3, giving us delta 2k times a sub k3. Summing over k gives us 0 plus 1 times 5 plus 0, which is 5. And look at that. That is exactly the A23 component of our original matrix.
All right, Section 4, Traces and Dot Products, Extracting Diagonals and Pairing Components.
This brings us to the real power of index contraction. You might remember the trace of a tensor A is just the sum of its diagonal components, a11 plus a22 plus a33. Well, in indicial notation, we can write this super cleanly as delta sub ij times a sub ij. Because of how the Kronecker delta works, this expression only survives when I equals j, leaving us with a sub ii. By contracting those matching indices, the Kronecker delta just wipes out all the off-diagonal terms to yield the trace. In our matrix example, that calculates to 2 plus 3 plus 6, giving us exactly 11. The exact same logic applies to vector operations. The delta perfectly pairs up corresponding vector components, streamlining a classic dot product into a nice, compact summation. The dot product of vector A and vector B is usually written as A sub I times B sub I, but we can express this using the Kronecker delta as delta sub ij times A sub I times B sub j. The delta actively picks out the equal indices, ensuring that component 1 of A multiplies component 1 of B, component 2 multiplies component 2, and so on. If we use our numerical example vectors, this evaluates to 2 times 0, plus -1 times 4, plus 3 times 1, seamlessly giving us a final dot product of -1.
Moving on to Section 5, Identities and Geometric Meaning, Core Rules and Spatial Intuition.
Okay, this slide right here, this is your ultimate cheat sheet for tensor algebra. Let's look at identity number 1, delta sub I equals 3. You really want to take special note of this one. Because of our implied summation convention, we are adding the 3 diagonal ones together. Delta 1, 1 plus delta 2, 2 plus delta 3, 3 equals 1 plus 1 plus 1, which is 3. Rule 2 tells us that composing the identity with itself, delta sub ij times delta sub jk, still gives you the identity, delta sub ik. For Rule 3, a double contraction of delta sub ij with delta sub ij leaves only the diagonal terms surviving, so the sum is again 3. Rule 4 shows that left multiplication by the identity leaves the tensor unchanged. And finally, Rule 5 shows that right multiplication does the exact same thing.
Now let's ground this in physical space. What does this actually look like? In tensor notation, the dot product of two basis vectors e sub I and e sub j equals delta sub ij. Geometrically, this symbol literally stores orthonormality. That means the same basis vector dotted with itself gives you a 1, while any perpendicular basis vectors give you a 0. For example, e1 dotted with e1 is 1, but e1 dotted with e2 is 0 because they're totally orthogonal in 3D Cartesian space. The Kronecker delta is the mathematical embodiment of a perpendicular unit-length coordinate system.
Almost done. Section 6, Common Mistakes and Summary, Guardrails for Index Notation.
Before you go off and start simplifying complex derivations on your own, we need to put up some guardrails. Let's review the 5 most common errors students make. Number 1, thinking delta sub ij is always 1. Remember, it's a matching game. It's 0 when the indices don't match. Number 2, forgetting your summation rules over repeated indices. Number 3, failing to distinguish between free indices, which absolutely must match on both sides of an equation, and dummy indices, which are summed over. Number 4, using one dummy index more than twice in a single term. Never do this. If you need to multiply more tensors, just introduce a new letter. And finally, number 5, do not confuse the symmetric Kronecker delta with the anti-symmetric Leibniz symbol. But hey, we'll save that one for a future explainer. If you remember absolutely nothing else from this breakdown, please remember this core principle. The Kronecker delta isn't just a neat math trick. It is the identity operator. It is your primary index substitution tool, and it serves as the absolute foundation of compact tensor notation. Mastering it means you master the language of continuum mechanics. So, here's my question for you. Now that you've upgraded from clunky matrix mechanics to sleek tensor calculus, how will you apply this sifting property to unlock your next major engineering proof? Whether you're calculating stress fields or fluid flows, always look for where you can swap, sum, or sift your indices to collapse massive equations into single, elegant terms. Thanks for joining me on this explainer, and keep exploring.